While you are working on the current problem of figuring out which products of powers of trig functions you can and cannot do by substitution, we want to look at another category of integration. Integrating rational functions, or what algebra means, we can stop caring at quadratic. So a rational function has the form p of x over q of x, where p of x and q of x are polynomials. Our strategy here is to build out a couple of core integrals that we'll just remember, and then use those core integrals to integrate everything else. So we're just going to take a few known integrals and include algebra, do some algebra stuff so that everything is in terms of these few known integrals. And some substitution, but easy substitution. Here are the algebraic things that we need. The algebraic things that we need are long division. We talked about this one briefly before. Long division is what we use when the degree of p of x is greater than the degree of q of x, or greater than or equal to. This is that improper fraction thing. If the degree of p of x is greater than the degree of q of x, we think of that as an improper fraction in terms of rational expressions or rational functions. And we can use long division to write it in its mixed number format, a polynomial plus a fraction, a polynomial plus a proper fraction. So that's the role of long division. We go from an improper fraction to a polynomial plus a proper fraction. This is the weirdest tool that we need. No, partial fraction copy. The most run-of-the-mill algebraic thing we need is completing the square. Completing the square is what we're going to apply to quadratics with complex zeros. So completing the square is what we're going to need to deal with quadratics with complex zeros, specifically quadratic denominators with complex zeros. Complete the square is what we use when we have quadratic denominators with complex zeros. This is also going to make us better at solving quadratic equations. Not that solving quadratic equations is something so critical that we need to be really good at, but at least when we get good at completing the square, we can dispense with the stupid quadratic formula. So in completing the square, what we do is we take a quadratic in standard form, ax squared plus bx plus c, and we rewrite it in a vertex form, a times x minus h squared plus k. This is our goal with completing the square. The third algebraic thing that we need is partial fraction decomposition. Partial fraction decomposition is what we're going to need if we have a quadratic denominator with real zeros, or the degree of the denominator is greater than 2. So partial fraction decomposition is what we're going to need if the degree of the denominator is greater than 2, or if we have a quadratic denominator with real zeros. That's when we're going to employ partial fraction decomposition. This is all just algebra. 2 old algebra things that we may or may not have forgotten, and 1 probably new algebra thing. For the most part, Calc 2 is the first time you see the algebraic process of partial fraction decomposition. But these are the things that will keep us from having to know anything about rational functions where anything is bigger than quadratic. Before we even begin, this is going to be kind of strange. And this is definitely when we're going to start thinking, man, when am I ever going to have to do this? To which my response is that's kind of not the point. It's not about doing these things. It's about learning how things are put together. This is a good environment for learning how fractions and therefore numbers are put together, and therefore better understanding how things work. I always like to remind people that before we start doing something that's fairly arcane and deep. And when people come along and say, oh, I can't believe your calculus teacher is doing this stuff. That's so outdated and old fashioned. Like, yeah, it is old fashioned, but keep in mind that person is literally advocating for you not knowing things. That's their argument. The argument is you shouldn't know this. And I think that's a dumb argument. You shouldn't know this is the first step to banning books. It's stupid. Anytime someone bans books, you should find out which books are being banned and go read them. They should move to the top of your list. It's like the Streisand effect, but literary form. Now, the problem is you probably won't want to know this once we get into it, which is acceptable. That I accept. You'd be like, oh, I don't want to know this. But as soon as you start being like, oh, I don't have to know this, I'll be like, oh, the fuck, how do you know? You know what I mean? I don't know either, but you don't know. Anyway. And I'm through with listening to businesses and what businesses want. Because I'm tired of feeding human beings into the grist that is just grinding out capitalism. Fuck you, businesses. Anyway, what are we talking about? I'm just kidding. Everybody calm down. Fuck. We're talking about integrating rational functions. We're integrating P of X over Q of X, where P of X and Q of X are polynomials. We're going to take a couple of core integrals that we'll recognize, and then we're going to apply these things to it so that we don't have to worry about anything bigger than quadratic. Now, the list of known integrals to make this work is rather extensive. It's kind of huge. There are 3 of them. That's how many we need to know. Those are our base model integrals. Here are our known integrals. Oh, choosing C was terrible. I'll make it an A. Changing a C into an A, that's a little bit pandering to a class of students. Will you always change C's into A's? Here's one of our known integrals. The integral of 1 over x minus a is natural log of absolute x minus a plus c. 2. The integral of 1 over x squared plus 1 is arctangent x plus c. And 3. The integral of x over x squared plus 1, this one's a substitution. This is going to be a 1/2 natural log x squared plus 1. So as far as categories go, This first one is just constant over linear, degree 0 over degree 1. This second category, 1 over x squared plus 1, that's a constant over quadratic, specifically quadratic with complex zeros. So this is degree 0 over degree 2. Degree 0 over degree 2 with complex zeros. And this last one is degree 1 over degree 2 with complex zeros. So we're going to learn to work with these. Once we learn these, once we remember these, this is going to be like our multiplication table that we learned back in arithmetic. We take the multiplication table that we learned in arithmetic, where we learned to multiply the digits, all the one-digit numbers, 1 through 9 times 1 through 9. When we learned all that and we used it as building blocks, we use that plus some algebra to learn how to multiply more digits. So this is like your multiplication table. This is your times table for integrating rational functions. Once we have these three, we could use these to build the other. The three algebraic tricks that we need are long division, completing the square, and partial fraction decomposition. Long division is when the degree of the numerator is greater than or equal to that of the denominator. Once we can take care of that, that's why degree 0 over degree 1, degree 0 over degree 2, degree 1 over degree 2. I always have the degree of the numerator strictly less than the degree of the denominator. Anything else, we're going to do long division until it looks like this, plus a polynomial. Partial fraction decomposition is for when the quadratic denominator has real zeros. Once again, we're already in the category of degree of numerator is strictly less than the degree of the denominator. So then if we look at the denominator and it's degree 3, partial fraction decomposition. If we look at the denominator and it's degree 2, but it has real zeros, partial fraction decomposition. And then finally completing the square, or for when we have degree 2 with complex zeros and an x term. So once we can deal with these three, we can deal with anything. How's everybody okay? I'm going to start with an addition problem. Take a minute I'll give you an entire minute to add these two fractions. There you go. We only started halfway, that's why we didn't get 4. I said 1 minute. So in case you need to work on timing, if you ever need to count like a minute just without a timer, remember Jeopardy think music, you get 30 seconds and it goes through 2, verses. So it's like da, 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 and then it ends with dun, da, dun, 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 dun. That's 15 seconds. So just get the timing right and you can mark out 15 seconds just by singing. So I don't know if that's ever going to be an issue, but there it is. So I said, you get 1 minute. You get 4 Jeopardy think musics. Because anything but metric system. All right. So if we want to add these fractions, we need to get a common denominator. So the first fraction needs the x plus 1. The second fraction is going to need an x minus 3. Then they'll have a common denominator. So the first fraction, 2, gets multiplied by x plus 1. And the second fraction, 5, gets multiplied by x minus 3. That will give them a common denominator. Now, when you did this, you started thinking, I'll cross multiply. Just don't say that word out loud in my presence. Cross multiply doesn't mean shit. It is a terrible phrase that gets used in multiple situations where fractions are involved. It's like the phrase canceling out. Oh, we'll cancel out these things. That's what leads people to dividing by 0 and starting to believe that 4 is equal to 5 and math is broken. They're just not following the rules. I mean, if you don't follow the rules of a system that's just explaining rules to you, then I don't even know what's wrong with you. So we get a common denominator, then we can multiply out the numerators. We get 2x plus 2. I can't remember everything, so I just have to write it down above. 2x plus 2 plus 5x minus 15. So I end up with 7x minus 13 over x squared minus 2x plus 3. So in this direction, all we did was add the fractions. So in this direction, we are adding fractions. To reverse this process is partial fraction decomposition. Reversing this process is called partial fraction decomposition, and that's what we want to learn how to do. One thing to note, when we're doing partial fraction decomposition, we're breaking things apart into terms. We're saying what two things add up to this result. So it's similar to factoring. What two things multiply to get this result? The difference is that when we have a product breaks into goes into factors uniquely. It's always, there's a very specific way that things break down into factors. But breaking down things into terms, we usually have an infinite way of doing it. 2 times 3 is equal to 6, and that's it. That's the prime factorization of 6. That's the only way to write 6 as a product of prime numbers. And if you have that product of prime numbers, you will only get 6. 2 times 3 is equal to 6. But there are lots of ways of writing 6 as a sum. 1 plus 5 is equal to 6. 2 plus 4 is equal to 6. 3 plus 3 is equal to 6. Negative 10 plus 16 is equal to 6. There's an infinite number of ways to write 6 as a sum. And that's what we're doing. In partial fraction decomposition, we are writing as a sum. So we have to pick which one we're writing. So the decomposition, we're decomposing a fraction into a sum. Here's why we would want to do this. I don't know why in Calc 2 has to be come in parentheses, but this is why we would want to do this, specifically in Calc 2, not just for funsies. In Calc 2, we want to do this because we would be given this fraction. We would notice that the not 13, it's 3. And it's minus 3. From a Calc 2 perspective, the reason that we would want to do this is that we would be trying to integrate some rational function, x squared, 7x minus 13 over x squared minus 2x minus 3. We would realize that the denominator is quadratic with real zeros. And so we would do partial fraction decomposition. And instead integrate 2 over x minus 3 plus 5 over x plus 1. So this is where we do the partial fraction decomposition. And the reason that we would want to do this is because these are two simple integrals that we could do just by looking at them. So this gives us 2 times the natural log of absolute x minus 3 plus 5 times the natural log of absolute x plus 1 plus c. What told us we had to do this is that we looked at our initial rational function, saw that the denominator was quadratic with real zeros, and that makes us do partial fraction decomposition. So we notice that the denominator is quadratic with real zeros. That makes it do partial fraction decomposition. We do that. We haven't learned that yet, but then we rewrite it as the sum, and the sum is made up of smaller integrals that we can just do by observation. We should also note that the denominator is quadratic with real zeros, which is what made us do partial fraction decomposition. We should also note that we decided to skip long division because the degree of the numerator was already less than that of the denominator. We should also point out the things that we're not doing. The notes that you don't play are just as important as the notes that you do. Let's talk about how partial fraction decomposition works. I'm going to remove the integration interface from what we're doing, and I'm just going to write down the fractions. So this is just something that's happening to the fractions. So the first step in partial fraction decomposition is deciding which sum we want to create. There's an infinite number of ways that we could write this fraction as a sum. We want a very specific one. So we're going to start by factoring the denominator. Start by factoring the denominator. This is us deciding which sum we're going to create. Out of the infinite number of sums that we can write, which one do we want? So step one, we factor the denominator. This is how we decide. Number two, each factor of the denominator creates a term in our sum. Each denominator or each factor of the denominator has a term in the sum. So one term will have a denominator of x plus 1, the other term will have a denominator of x minus 3. If I had a third factor in the denominator, I would have a third term. Next, we remember the form. We're only ever going to have degree 0 over degree 1. The degree of the numerator is start off less than the denominator, degree 1 over degree 2. It can't be from a sum where the degree of the numerator is going to be greater than that of the denominator, unless some stuff is canceling out and we're writing an excessive sum. So, third, we put in generic numerators. Since the degree of the denominator is 1, the numerator has to be degree 0. So third, generic numerators. That's the setup. Start by factoring your denominator. Each factor of the denominator corresponds to a term in the sum. Then you fill in generic numerators. Then you just make this happen. Figure out what A and B are. Once we have this fourth, now we can find A and B. To do that, we just add the fractions. So for our x terms, I have a plus b is multiplied by x. And for a constant, I have negative 3a plus b. The standard way of doing this is to add those fractions. Once you have set up after step 3, you have your generic numerator, add the fractions, and then set up a system of equations. So notice that 7x minus 13 has to equal a plus b times x plus negative 3a plus b. That means that the coefficient of x, a plus b, must be equal to 7. So this means that a plus b is equal to 7. And this must mean that negative 3a plus b must be equal to negative 13. The constant of this numerator, the numerator, must be the constant of the numerator. Oh, negative 13. The coefficient of x of the numerator must equal the coefficient of x of the numerator. And this leads to the solution. A is 2, or A is over x plus 1. So A is 5, and B is equal to 2. There is a shortcut for solving this system that we'll have to talk about tomorrow. But wait, there's more. There is a shortcut to solving the system. We'll talk about that tomorrow, but that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day and thanks for playing.